All right, it's 8 o'clock here on the Pacific Coast. Let's get started. Good morning, good afternoon, good evening, everyone, from wherever you're joining us from. Welcome to the next installment of tinyML Talks. Today we have Charbel Rizk, founder, CEO of Oculi Inc., to talk about Oculi is putting the human eye in AI. My name is Ravi Sivalingam from Qualcomm AI Research, and I'll be your moderator today. We'd like to thank our tinyML Talk strategic partners, Aeon Devices, ARM, DeepLight, Edge Impulse, Emza Visual Sense, Foda Hub, Greenwaves Technologies, Gravity Inc., HOTG, ImageBob, Itemis, ClickerTech, Global IoT Solutions, Latent AI, Maxim Integrated, Micro.ai, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renesas, Rexen Technology, SAP, Seed Studio, SensiML, ST, StreamAnalyze, SynSense, and Sentient. Additional sponsorships are available. Please contact Olga at tinyml.org for more info. Just a reminder that the tinyML Summit 2022 is going to be in person on March 28th to 30th at the Hyatt Regency in San Francisco Airport. The tinyML Research Symposium is going to be on March 28th. I think the registration links are posted here. You can check it out on the slides. Also a reminder of our live online upcoming event, the tinyML Trailblazer series, Success Stories with Joel Rubino, the CEO and co-founder of Cartesium, moderated by Chris Rowan. Our tinyML communities are growing very rapidly. We have over 7,800 members in 42 groups in 33 countries on meetup.com. And our LinkedIn community has over 2,500 members and 4,400 followers. Please use the links or the QR codes to join our community. Also, our YouTube channel is up and running with over 337 videos and 5,900 subscribers. You can subscribe to the YouTube channel for updates and notifications, including when this video gets posted. Our next event is going to be on Tuesday, February 1 by Mohammed Shafiq, New York University of Abu Dhabi, UAE, to talk about energy efficiency and security for tinyML and Edge AI, a cross-layer approach. The webcast start time is the same time, 8 a.m. Pacific. Please contact talks@tinyml.org if you're interested in presenting at an upcoming event. Okay. Yep. Today we have Dr. Charbel Rizk. He's a co-founder, founder, CEO, CTO of Oculi, and an associate research professor at Johns Hopkins PCE. He has been recognized as a top innovator, thought leader, and successful principal investigator, S&T manager. He was a pioneer in autonomous systems and led a small team that developed and demonstrated the first four-rotor, quad-rotor UAV system in the early 90s. Dr. Rizk has successfully collaborated with various FFRDCs, government labs, academia, and industry of various sizes. He's a senior member of IEEE, AIAA, and a member of AUVSI, EAA, and OSA. Take it away, Dr. Rizk.
Thank you very much, Ravi. Hello, everyone. I wanted to first off, give you a quick summary on the technology that we've been developing. But before I give you more details, I really wanted to make one disclosure that I have been a user and a consumer of vision technology for most of my career. And I created this long list of, I wish I can do this, I wish I can do that. So what Oculi is trying to commercialize is really kind of the summary of all these, wish lists that we collected over time. And what we developed at the end of the day is a single chip vision sensor that is software defined. Every aspect of it is programmable, and I'll show you examples of that. We believe also that we have implemented an architecture that is very efficient to where that, when it is part of a product or a solution, we will deliver significant gain in both time and energy. And the technical term that is typically used is the energy delay product. We have, as Oculi now, we have hardware on hand that has been tested and validated with customer projects. And we have a pretty strong IP portfolio that go with it. Our initial market focus is on XR and interactive and smart display But as many of you probably are active in many other markets and applications involving vision technology, you'll have an appreciation that this technology would be relevant in a wider market. And so before I move on, again, sometimes it gets missed somewhere in the presentation or in the discussions. We're not building a sensor chip. We're not building a processor chip. We have really developed a new architecture for vision technology where we integrated both the sensing and the processing at the pixel level. And we call our chip the SPU, Sensing and Processing Unit. To kind of give you again, reiterate the motivation why we did what we did. Again, I've been a consumer and a user of machine vision, computer vision for many years. And we continue to do machine vision for the most part the same way. We basically have a sensor that dumps lots of data, and we develop a processing, a platform and algorithms that take that data and output the actionable information. And what we have done over the years, we simply increased the number of pixels on the sensor, the resolution on the sensor. We also increased the horsepower on the processing, but we continue doing the same thing, okay? And that's really a very inefficient way of doing vision. And what we have been going after, and for the obvious reasons, is try to develop machine vision to mimic, to some extent, human vision, because it is very efficient. And if you look at the human eye, it has orders of magnitude more resolution than even some of our best cameras today. Yet they only output a maximum of 10 megabits per second to the brain. And that's because the eye does a lot of upfront pre-processing and does it in parallel and very efficiently. And it outputs only the relevant information to the brain. That's what we call vision intelligence. And that's what we're after right now. We're after building sensors that output vision intelligence, and they're also software programmable to allow for continuous optimization, because literally that's what the human vision does. It's not a one-way, the sensor dumps data on the processor. It's actually a feedback signal that's continuously operating to optimize the solution. That's why human vision can do very complex tasks only using a few milliwatts, and it does it in real time. So what we have done in Oculi is basically build a single chip a vision sensor that operates kind of like the eye in some key aspects, which is it has enough smarts to output vision intelligence, but it also receives external signals to continuously adjust and adapt and to optimize the solution. So we can eventually deliver now machine vision that operates in milliwatts and also operate in real time. Okay, that's the combination that hasn't been possible before. You have to give up either you have to consume either more power or generate more latency. Okay, now we believe we have an architecture and technology that can afford you both. And the reason why we're excited about the tinyML community and what the foundation is trying to do is because we have brought machine vision now to the point where it is so efficient it can be implemented in a tinyML architecture. And so the basic SPU architecture it would look like, again, this is a picture on the top left, one of our imaging sensors and one of our SPUs. It looks like any other imaging sensor. It's an array of pixels, except in our case, every pixel now embeds in addition to the sensor, it embeds digital processing logic and a little bit of memory. So every pixel becomes smart enough now to be programmed to do some computation and outputs information that's more relevant. Okay. And so the examples that you see on the right side there, those are 4 different outputs that you get out of the SPU. Those are all, again, programmable. You can get full frame video like every other sensor that everybody has been using for a long time. But you can also start getting less and less data, but more information, down to what we call the actionable information or actionable signal. And that's the least amount of really data that the SPU generates, but still has enough information to act on it. We developed the architecture to be agnostic to the sensors. So we have demonstrated the SPU with CMOS sensors as well as infrared, and we can also do the same with depth. Okay, and there's also a unique IP and technology that within Oculi that we've developed, where the sensor pixel, can operate both in camera mode, kind of color imaging mode, as well as depth. Okay, so in a nutshell, really, that's what Oculi has been after, trying to simplify really machine vision and make it efficient without sacrificing some of the key aspects: accuracy, latency. Okay, so any questions? Because I prefer more an interactive discussion than for me to go through the whole presentation and then at the end answer questions. So if you have any questions, by all means, pause it and jump in anytime. Okay.
Sure. Actually, there's one question about slide 12, just the previous slide, about why the transfer between the perceive and sense is bidirectional.
The transfer between the perceive is bidirectional?
Yeah.
Oh, that's the key aspect of allowing. So let's say you're looking for certain things in the scene, and all of a sudden the scene changes or the requirements changes. That allows you to control the sensor to change the way it operates to optimize for the solution that you're after at that particular time, right? And I'll give you a list of aspects of the various aspects of the sensor, and I can give you the example of that people use nowadays for dynamic range. When let's say you're driving and when you go into a tunnel and out of a tunnel, the lighting conditions change significantly, right? So this allows the dynamic range to be adjusted based on the environment, right? But you can do the same also on the selection, right? You may be looking for fast moving objects, and all of a sudden you want to look for slow moving objects. So you change the control signals to change the selectivity involved. Okay.
That makes sense. There's one other questions I have in the next slide. I don't know if you're going to cover this later. I mean, it makes sense to move the compute closer to the sensor, to the pixel, right? Because that's some of what people call like early vision or low-level vision. It makes sense to do that earlier, so maybe even reduces the amount of communication that goes to further and processing for higher-level tasks.
Yeah.
So, but given how kind of standardized, and I probably shouldn't say commoditized, but the manufacturing of sensors has become, did you run into any manufacturability issues with some of these things?
No, I mean, we have been able to produce and design with standard CMOS processes. So it's basically adding more transistors in the pixels. We're not asking for any unique processor, any unique, because that defeats the purpose, because you're absolutely right. Anytime you do a custom solution, the cost, at least in this technology, grows fast. Mm-hmm. So we basically have been able to demonstrate with standard CMOS processes.
Okay. Thank you. That's all the questions we have now.
Okay, great. Okay, so just to kind of give you a quick example, because that would probably be quicker and faster than describing it with words. We had a customer in the transportation space, and we deployed our sensors on a public freeway, and the customer now any combination, at any given time. The first one being a full frame, and that's really been the biggest challenge with vision technology, right? It's a gigabyte problem, right? Even if you're running at 30 hertz, you are generating a lot of data, and most of the data is not really relevant. Like in this case, the customer cares about counting axles. So the second video from the left is where we output only the pixels that are changing. So that's typically, those of you who are familiar with event sensing, that's typically the only output you get from that type of technology. The third video is what we call smart events, and that's where we program the pixels to not, to pick out really the events that are of interest to that particular application. In this case, we care about obviously the vehicles and particularly the wheels, right? And so we reduce now the bandwidth from 30% down to 3%. That's a factor of 10. And then we can even go one step further in the SPU where we output the a signal that corresponds to the axle. And again, that's a reduction of the bandwidth down to almost zero. So you take a problem, right, in machine vision that starts today typically with gigabytes of data, and then we simplify it down to a few bytes of data. And this is why we wanted to really share our technology and our story with the tinyML community, because then you can imagine that, many other applications around this capability. So we talked about being software defined, and I basically wanted to spell out that, every aspect of the sensor, again, as a user, over the years, I came up with the wish list and I tried to implement it in this technology. Because many times we build a solution around a vision technology or vision sensors, and we really say, I wish I could do this, right? So that's basically what we attempted to do here, okay? It's not a Swiss Army knife. It's actually a bit more optimized for, application specific, set of applications. But as you can see from this list, every aspect of the sensor is programmable and can happen in real time and dynamically, okay? And that gives you a lot of flexibility, because I can see, for example, as watching some of the presentations that have gone past on tinyML, I can see where they take, for example, a color image and they, bring it down to 8 bits. Again, for the obvious reason, they want to reduce the number of data that is involved. That's a simple example of what we can do. You can pick the number of bits that you want to use in that particular application. You don't have to change the hardware. This is all done with software and at the pixel level. The reduction in data starts at the pixel, okay? And that's really why we can deliver, a significant gain in the overall, solution. And this is how we fit into that bigger picture. So many of you are spending a lot of, time and focus on making machine learning more efficient, and you can implement on smaller and smaller processing platforms, which is great for us. It's really music to our ears, because we have really solved that problem at the sensor level. So combining the two would really now deliver solutions in machine vision that are not possible otherwise without the combination of those two technologies. And again, I'm showing and highlighting the feedback signal that exists in our SPU, because nothing is frozen, nothing is hardwired in the way it operates, and it can dynamically adjust as needed. Okay, so that's kind of the overall picture for how we see our technology fitting into solutions and products in the future. Any questions by any means? Again, I'm reminding everyone to stop me anytime, and I'm happy to take questions. This is again, I'm going back between, to some, hardcore technical data, or at least information. So all of us who have played in the world of sensing and processing, and specifically vision sensing, have learned the basic trade-offs that exist here between latency, power, and bandwidth. So everybody likes to put cameras on board their systems to add more smarts for the obvious reasons, right? They provide a lot of information versus other sensing modalities like acoustics or RF, right? Cameras generate a lot of information, but the curse of cameras is that they generate a lot of data that is also not very good, right? And so that's why we've all lived in that trade space, and we have to constantly, trade off. The Oculi technology, was developed really to allow you flexibility in that trade space. Whenever you need more data, then you get it. Whenever you need less data, then you get it, and then you benefit accordingly, right? Both in latency and in power. So you no longer have to build a solution today that is a single point, single operating point. You can now build a solution that can actually change depending on your requirements. I won't dwell on this chart too much, but in a nutshell, everybody else, it doesn't matter what technology they're using today, has to move a number of data bits before processing takes place, and then you reduce the amount of data to simplify the problem. In our case, we actually do that processing right at the capture point and move and further process a lot less data. That's really where we get our gain both in latency and in power. Okay. Our architecture involves multiple pieces. One of the key aspect of the architecture is what we call the IntelliPixel, and what we have embedded in the pixel itself. So you basically have a photocurrent that comes from the sensor, from the photodiode, and then we take that signal, we digitize it, and then we have the ability to do the basic computation and a little bit of logic and a little bit of memory. That's basically what we formed up to make the IntelliPixel. It has enough smarts to make a decision that whether that pixel is sensing a signal of interest or not. And I'll show you even more examples of that. This is a group of examples that we're doing with one of the customers. I'm showing you, in this case, kind of a solution examples, but we're looking to really collaborate and partner with, many of you to develop even more solutions. These are, call them the tip of the iceberg. So in this example that just played, our engineer is demonstrating touchless screen control. So we basically have the SPU tracking his gesture and controlling the screen. Okay, so that's kind of a solution demo that we did. Similarly, on the bottom, we did eye tracking. Again, we're not the first ones. I'm sure all of you may, or some of you may have done applications like that. We're not the first ones to demonstrate this capability by any means, but we are the first to demonstrate it so efficiently and on potentially a single chip solution like the SPU. The bottom left is really eye tracking. Again, we're showing you what we call the smart events, which is only 2% of the overall data that you would otherwise get if you're using a full frame, imaging sensor. We're reducing that amount of data by a factor of 50 and still enough to effectively track the eye and in real time. In this case, we can do eye tracking in hundreds of hertz, kilohertz, whatever, there's really no upper speed limit, practical speed limit on this technology anymore, because you can run very fast, but you're still outputting only a small amount of data. To build on that, right, we demonstrated high-speed depth using 2 SPUs. Now, the computation for stereo vision were done on the smart events, not on the full frame. So those of you who have done stereo vision will have an appreciation that the amount of reduction, you can see the bandwidth hovering around 1 to 2%. And in this case, we're obviously doing 3D, high-speed 3D gesture tracking, and then again, I can give you more examples, but in the interest of time, because I'd like to really have more discussion, I'm moving on now to, what we're looking to do and hopefully make happen soon within this community, which is we've been focusing really more on solving the sensor limitations, and I believe we're there now. And now we're starting to turn more of our attention to what do we do with this kind of capability. So what I'm showing you here is, as you can see, a full frame video and then a smart event output. And what we basically used a trained ML model on full frames. We didn't do anything to the model. We just grabbed it, and now we're running full frame through it, and it's showing you how well it's working in detecting people. And then we're taking the same model without doing anything to it and feeding it now smart events instead of a full frame video. And we're showing you the accuracy of that model. And in fact, surprisingly, there are some cases where the smart events have better outcome than full frame. because you're feeding it really less noise. So that's not surprising to me. Now, in other cases, you may end up missing some detections because you don't provide enough data. However, our technology will prevent that a problem in a final solution setting, because you can quickly and in real time adjust the settings to increase the number of pixels coming out up to a full frame. It's really a continuous adjustments. It can go down to actionable signal all the way up to full frame and everything in between. It's a smooth and continuous. And again, we're looking for finding collaborators and partners to start working the second piece of this pie. And in this case, we're counting people going into a conference room. Again, it's the same concept. We took a trained model, that same model, and we used full frame on it, as well as we used smart events. I apologize if the videos are flickering on your side. It's the Zoom link. I'm assuming there's a good number of people on the meeting, and maybe the bandwidth is struggling. But in this case, you really, you have a one-to-one match, because this is a relatively easier problem. But again, I would highlight the bandwidth reduction. So you're doing the same thing now with a lot less data using the same trained model. So any questions so far before I kind of go on to the next level of where I want this community to eventually, get excited about?
Yep, absolutely. There are actually quite a few questions that have come up. One is asking, actually a pretty broad question, I guess, but what is the accuracy level for Oculi technology? And I guess to kind of further enhance the question, I'd like to ask, like maybe on a specific task, like what you had shown for human detection, right? It wasn't very clear from the plot, I know partly with the Zoom bandwidth issues. But if you don't retrain versus you retrain on smart events kind of images, like are you able to fully recover the accuracy that you're getting for, let's say, human detection?
Yeah, if we retrain, we haven't done that yet, because again, we're more on the sensor and the hardware side, and we're looking to team up with the community here who have been focusing more on the machine learning side, right? So we haven't really dug in too much on that one, but I can tell you intuitively and from experience, because I've lived in that machine learning space for a long time, that if you retrain on smart events, you're definitely going to get better results. Because the whole point of smart events is to extract the background noise, anything that's not relevant, right? And so now without retraining, we really did a quick run on that example, or a couple of examples. Before we can tell you what the accuracy reduction will be, or changes, I should say, we obviously need a bit more, examples and cases, right? And so we're just showing you that, we are looking for, partnering opportunity to start moving in that direction now. Okay.
Got it. I have another question. Since you're looking at these smart events, that means you're kind of inherently assuming that the interesting events are always moving. But what if there are static, things that you want to detect that are also static in the scene?
Okay, very good, Ravi. You set me up good for hopefully what's coming up next. That's one actually key aspect of our technology, is that your smart events are not only dependent on motion. They can be based on color, they can be based on pattern, on size. So you have the ability to do that, and I'll show you a couple of examples of that.
Okay, got it.
Yeah.
There's another question in the ML backend. I'm not sure if I fully understand the question. Are the ML backend in eye tracking and face detection, or only SPU processing? So I'm not sure I fully understand it, but
no, I think I understood the question. So the examples we showed actually involved a little bit of external processing beyond the SPU. And the reason why I'm sharing it with the community is because those are applications that are ideal for tinyML. That by the time you get the SPU signals, both the smart events and what we call the actionable signal, the combination is still not a lot of data, and they're ideal to do a machine learning on in a tiny environment. Okay.
Got it.
And this is really what, a good question on the video that has been playing here for a bit. So if you all focus on the third video, what we call the actionable signal, that's really the least amount of data we can output from the SPU, but you can see there's enough information there to potentially train on it, right? And again, this is where we would love to, partner with folks on doing exactly that, developing machine learning on that type of signal, or it could be a combination of the three, right? So that the key aspect of the SPU, not to get lost, you can get any of those outputs in real time, right? So your learning can go from the actionable signal to smart events to full frame and back as needed. So if your confidence level is low, you start getting more data. And if your confidence level is high, you don't need any more data, right? That's the part of, you asked me earlier, Ravi, what's the feedback signal for? That's a perfect example of that, right? You're continuously adjusting how much data you're getting off of the SPU based on what you're trying to accomplish, okay?
Got it.
And
I'll let you proceed and we can get more questions later.
Sure. Thank you. And so you asked me earlier about whether we only look for, motion, which, and I wanted to highlight that you can actually do spatial filtering based on any pattern. So we're showing you kind of a few examples because, every pixel has a memory. So you can program it and you can extract any pattern that you want, in real time and very efficiently. And again, I don't know how many in the tinyML community dreamed of doing high-speed imaging using a tinyML platform. What I'm telling you here today, you can do it with the SPU technology. We're doing here a gun flash capture. We actually can run fast enough to capture the bullet in flight, but we're still only outputting a little bit of data. As you can see, if you are trying to do this demo with full frame, you'll be generating 120 gigabytes per second. We program the SPU to only output the gun flash and bullet information, and now you're down to 10 megabytes per second. So that's not, that's a manageable amount of data bandwidth that you could use in a tinyML environment. So what I want to make sure I don't leave is to don't constrain yourself anymore in thinking of solutions and products based on conventional sensing and vision technology. I believe we really have solved some of the key bottlenecks and start thinking, even bigger. And so high-speed imaging is only one example. Can you imagine, a very small module, that's doing high-speed imaging and perception, and I believe we can get there. And this is really an example of that. In this example, we were trying to demonstrate that we can detect the type of gun, so not only do we detect a gun flash, and we can actually, from the signature, figure out the type of gun. And I believe that is doable in a tinyML environment. So the second area that I want to also leave with you is that, as I mentioned before, we developed a unique IP to allow each pixel to do both color and depth. So this is an example of the video that's playing right now, where the smart events are coming out based on the change in value, both in color and in depth. Okay, and so don't limit yourself to color imaging is what I'm saying. Start thinking also of applications involving depth or both. Okay, and again, we can simplify your problem because we can output a lot less data and make the solution. The bottom video example is showing you, again, smart events, but instead of motion, it's based on value. So you can see the hand, if I can stop the top one again and play it for you, if you look at the right video on the bottom, right, it's showing you the hand coming in and going, and that's because we have smart events based on depth. So whenever the hand is within a certain distance of the sensor, it becomes visible, and otherwise we ignore it, right? And the same thing on the left side is based on color, okay? And so again, come to us if you have a great idea, a great product that you envision and you've been limited by the sensor side of the solution, we believe we may be able to help. And to make life easy for you, we have actually a relatively easy to a platform for you to use. This one is available only for the color imaging SPU. We don't have the depth dual mode available yet, but you can, it's the same concept. So once you get a feel for it in one modality, it transitions, the same to depth. But this platform is available. We have more demand on it than actually supply. So we are looking for selective partnership here to allow you to really experience the benefit of this technology. The lawyers tell me I have to include the boring part of the presentation, and I'm pretty much done. I wanted to leave time for more questions, more interactions. So I'm happy to answer.
Absolutely, thank you. And by the way, sorry, I have been getting disconnected from Zoom for some reason multiple times during the presentation, so I may have lost some of the questions that I can see from my Q&A window. So Evgeny, please feel free to jump in if there are any questions that are there that I cannot see. But at least one that I have on my screen right now is from Wayne Book. Does the technology require initial treatment with more conventional image processing or machine learning before applying any convolutional neural networks type processing?
Yeah, I don't think I followed the question, but there's no really a prerequisite if that's the question. You get the native image data that you have been getting from a conventional sensor. You get if you want, you get pixel intensity, location of the pixel. You get some time associated with it. So there is nothing really different than what you've been doing for a long time.
So there are a couple of questions also on the chat, Ravi. David is asking, do you program the processing logic via an SDK? Is there any SDK you can offer for developers to do things?
Yes, it is definitely. We have an SDK that goes with the platform. Correct. Yep.
And is it available for people? How do they get hold of it if they want to?
Yes. So whenever we work with an entity, we basically give you the hardware and the firmware/software that goes with it. Correct. And we also have documentation, kind of a user manual as well. Okay.
There is one new message. Oh, there is a question from Oculi. How much does it cost?
I can look at I think I can see the chat box too. I could, if I can help you guys here. How much does it cost?
Yeah.
Oh, okay. It's negotiable.
There is a question. There are a couple of questions in the Q&A, Ravi. Do you see them? Or you're still having issues with Zoom?
I'm actually scrolling back. Are you guys looking at the Q&A or the chat? Because I see some questions on the chat.
Q&A, yeah. I think it looks like Ravi is.
Ravi is still trying
some
to
issues
fix
with
this
Zoom.
connection.
So maybe let me take it over from here. So Samir is asking, what is the main use case? What applications? What applications you kind of see this type of technology in volume?
We're focused on edge applications, and as I mentioned earlier, the initial focus is on XR, AR, VR space, as well as interactive and smart display. But in general, really, anytime you're constrained by power, latency, cost, size, we definitely can offer a very competitive solution.
Okay. There's a question from Kelvin. can you show some example code on how to program it? I don't think we have time to go through the example code, but maybe can you describe a philosophy, how people can code on the sensor?
Yeah, so the S11, which is the prototype that we have now available, is has it's all digital interface. So every pixel has a unique address. So you can select that pixel and write into the memory or read out of the memory in it, and the logic as well. You can program it accordingly. So we have scripts for you, so you don't necessarily have to worry about that. We have developed a VHDL, and because the platform that we have available now, we have an FPGA to do the interface with the SPU, and so we have scripts that allow you to read and write and then change between the various modality.
There is a question from Pritam. Can the SPU work standalone, or it requires supporting processor chip?
So some applications, again, depending on the requirement, there are some applications where the SPU would be enough by itself, and then there are also many applications where an external processor would be needed.
Okay. There is a question from Corentin. How does performing the analog to digital conversion at the pixel level impact the area efficiency compared to the standard column-based techniques for image sensors?
Good. I mean, a good question. I mean, there's definitely more area usage when you add more functionality in the pixel. Now we use a sigma delta, and the footprint for it is small. That's basically what we do. But yeah, definitely there is. If it was all great news, then I'll be lying to you, right? There's always going to be some trade-off. So we do use up more space in the pixel. But the trend that we predicted many years ago, and it's really moving in our direction, is that we're able to do more and more with smaller pixels now. So I see a question on latency.
Yeah, there is a question. What is the latency of the smart event?
Yeah. There's really no latency on the smart events because everything is happening at the same time. The whole SPU, all the pixels are processing at the same time. There's really no serial processing taking place. And so the gun flash detection that I showed you obviously was running and very fast and outputting the pixel and we have also demonstrated ranging to also prove the point of latency. We integrated the SPU with a laser that we were modulating, and we can estimate depth because we were running the pixel at I believe 128 megahertz. So we have the speed, and everything is running at that speed, by the way. So there's really no practical latency to speak of. Now it depends on, again, we don't do magic, right? So if you have more smart events, so you have to control the number of smart events because eventually you can't output data fast enough, right? So the SPU can run very fast and it does things in parallel, and there's really no practical lag or latency there. But then as you start sending people, data off the chip, then we have the same, I/O limitations like everybody else. Okay.
Yeah, no, this is very remarkable. I mean, in the example you showed of the gunshot and the bullet tracing, that's amazing.
Yeah.
What you can do with this technology. So Charbel, you have very strong ties to the academia, kind of by your background and by your training and by your heart. There is a question from Brian. Does Oculi collaborate with the research institution, and who would be the contact for inquiries in this direction? Because again, the technology is so cool. I'm sure many people in the academia would like to get hold of it. So how do they do it?
Yeah, we actually have 2 active collaborations right now with the universities, and we're happy to have more. Just shoot me an email and I'll connect depending where you are and what time zone, because we are a small company, but we have actually operations internationally as well, in addition to the US. So depending on your time zone, I'll connect you with the right individual on our team. Okay.
Yeah, and I think somewhat related to this question on the chat, more for developer type of people. can it interface with Raspberry Pi or Google Coral or Jetson Nano or kind of any of those more traditional, more conventional boards for people?
Yeah, I mean, right now we have USB and we have Ethernet interfaces on the board that I showed earlier, and so yeah, we have built actually I just remembered now the sensors we deployed on the freeway that I showed earlier in the presentation. They had a Raspberry Pi as the interface to the network, and because we were controlling the sensors remotely and getting data from them remotely from our office. So we use the Raspberry Pi as the interface.
Oh, that's very convenient for people to use. That's obviously very popular platform for developers.
Yep.
There are a couple more questions on the Q&A. Question from Sudha. Does processing at pixel level create an overhead in terms of size? I think you answered it before, but maybe can you quantify it? Like, how does it? What is the penalty?
Yeah, I mean, it's we need to put more transistors there, right? Like I said, I'll be lying to you. We don't do magic. We haven't violated physics either. So the trade-off in our mind anyway has proven to be acceptable. And as you go to more advanced nodes, that area again, the penalty for it shrinks as well. I'm happy to. We have fabricated multiple chips. And when I say we have done this, by the way, I should have made that disclaimer early on. Not everything that we have now and we are using has been done, through Oculi. A lot of that was done in my previous life, but it was, it's part of the startup deal that we made with the university. So we have access to it, and so, but we have fabricated down to 16 nanometer node. And and demonstrated how we can shrink the size significantly. And as you go to even more advanced nodes beside the 16, then you get even smaller and smaller footprint. And so that's the reason really why early on we made the decision to make the Pixel mostly digital, because we wanted to scale with the process.
Yeah.
If it was mostly analog, it doesn't scale with the process, and you have all kinds of issues. So we made our Pixel intentionally mostly digital to scale with the process. Okay.
Yeah, that's definitely a wise strategic decision. And I think on top of this, as you know, big foundries like TSMC and so on, they offer now Pixel PDKs down to very, very advanced technology nodes. So you can definitely add more digital logic there without sacrificing area too much. There is always a little bit of a penalty, but now it's kind of becoming more acceptable. And it looks like we have our last question from Ali. For this model, how is the data stored and transformed? I'm not sure what model he's referring to, but in general, what is the process of data storage and transfer kind of once you acquire it from the sensor and do processing there? What is the pipeline, effectively, kind of the data pipeline?
Yeah, I'm struggling with that question myself as well. The example I showed earlier really was a kind of a standard trained machine learning model that we grabbed off of open source, and we were simply feeding it the smart events instead of a full frame video. And now you see, if the question is more about the spatial filtering, we have a small block of memory in every pixel. That's typically where you store, the value if you want to do any spatial filtering, and so I hope I answered the right question.
Yeah, and somewhat related to this, I'm just curious, in terms of standard image sensor processing, like some ISP functions, how do you do those? Like if you want to do some correction or filtering?
Yeah, we do. Again, that's why we have implemented. You have the ability to do the basic computation, and you have a little bit of memory, and so those are your only constraints, and then so you can implement any computation at the pixel level that doesn't require more than that. Okay.
Okay. Sounds good. Well, thank you, Charbel, for this excellent and exciting presentation. I hope the audience got a taste of what this advanced technology can do, and I think this is just the beginning of like what can be done with this advanced vision is this field. There are many applications coming, and also a lot of things like advanced processing and advanced technology nodes. I think that's actually an exciting field, and more software development and SDK. So I'm sure your team is quite busy talking to customers and exploring all of these different use cases and different opportunities there. Yeah, thank you.
Yep. Thank you, Evgeny. Thank you for the community, and I'm a big fan of what you, Evgeny, and everyone else has been trying to do, and I hope we grow our footprint and presence in this community soon.
Yeah, I think as we know, vision is huge. I mean, human perception, 80% of human perception comes through our eyes. So
yeah.
if we can augment them in a good way and kind of make use of this, that would be super powerful. Yeah, so let's acknowledge our sponsors one more time. So it's the AON Devices, ARM, DeepLight, Edge Impulse, Emza, PhotoHub, Greenwave Technologies, Gravity, Hodge, ImageLab, Artemis, TOOLKIT, Latent AI, Maxim Integrated, which is part of all devices now, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renaissance, Rixen, SAP, Seed, tinyML, STMicro, StreamAnalyze, SynSense, and Symbian. And again, we're going to have tinyML Summit in person in the end of March. So all these companies will be there showcasing their products, and this will be a great opportunity to talk to them live and shake people's hands there. And then finally, just quickly, let's acknowledge the executive sponsors. The executive sponsors are ARM, the software and hardware foundation for tinyML. Then we have Edge Impulse, the leading edge ML platform. And Qualcomm, advancing AI research to make efficient AI ubiquitous. Symbian, end-to-end deployment solutions for tinyML and Edge AI. And then the platinum sponsors, DeepLight, they use AI to make other AI faster, smarter, smaller, and more power efficient. TOOLKIT, global IoT solutions. Reality AI, add advanced sensing to your product with Edge AI tinyML. Renaissance, it's a leading microcontroller and microprocessor company. They have a broad and scalable edge computing portfolio. And the gold partners are PhotoHub, Maxim Integrated, Latent AI, Adaptive AI for the intelligent age, Micro AI, and NXP, Heat Studio, tinyML, build smart IoT sensor device from data, ST Microelectronics, and SynSense, they build sensing and inference hardware for ultra-low power embedded using neuromorphic computing. And this is the list of silver partners. Thank you again for joining today. Thank you, Charbel, for the excellent presentation and sharing your wisdom with the community and providing your contact information. I'm sure people will contact you afterwards, and we hope to see all of you live in 3D, in person, in 2 months at the summit.